Mahalo. All right, so welcome to my talk on XPC and a bug named root pipe. As he mentioned, my name is Patrick. I have worked at a bunch of acronymed places. I'm currently the director of R&D at Synac. So Synac does crowdsourced vulnerability discovery with vetted security researchers. Basically, anyone can sign up to find bugs in our customers' websites, mobile apps, IoT devices, and even networks. Our customer security isn't that good, so we end up paying out a lot of money to our researchers, which I think is pretty cool. So if this is something that's of interest to you, check out synac.com or come chat to me after the talk. All right, so what is this talk going to cover? We're going to start with a brief overview of XPC. We're then going to talk about a privilege escalation bug that was named root pipe. We're going to talk about some malware that was then discovered that actually preceded the public disclosure of the bug, and so it was exploiting it as a 0-day. We're then going to talk about Apple's initial patch, how they blotched that patch, how I was able to bypass that to re-exploit the vulnerability on a fully patched system, and then briefly talk about Apple's final patch, which seems to maybe squash the bug. All right, so usually credits are given at the end, but there are a lot of really good OS X security researchers who I've learned a lot and who are kind of partially responsible for the content of this talk, so I just wanted to acknowledge them up front. So first is Ian Beer. He works at Google Project Zero. He's given a lot of talks on XPC, found a lot of really cool bugs. So pretty much everything I've learned about XPC is from Ian. Emil, who has a last name that I don't know how to pronounce, actually found root pipe, so obviously a lot of credit goes to him as well. And then Pedro, he did some initial analysis on Apple's original patch, which kind of got me inspired to look at it a little more. And then finally, the book that taught me most of what I know about OS X internals was written by Jonathan Levin. So if you guys are kind of interested in this, I would highly recommend this book. All right, before diving in, since we're in Vegas, I think it's good to define any possibly ambiguous terms. So in the context of this presentation, when I'm talking about implants, I'm talking about malicious persistent code. I'm talking about hooking, I'm talking about intercepting function calls, installing a hook or a detour. A Trojan is a malicious program, something that is, malicious but pretends to be benign. And then injection is all about getting code into a remote process. And then finally, a backdoor in the context of this presentation is code that provides undetected remote control of a computer. All right, so with those out of the way, I want to start with a brief overview of XPC, which is a modern inter-process communication mechanism on OS X. Since root pipe is an XPC-related vulnerability, I think it's important to understand what XPC is and how it works. So XPC, as I mentioned, is an IPC mechanism with two goals: privilege separation and stability or fault tolerance. So basically, each XPC component is its own unique process. So this allows, obviously, a lot more fine-grained controls because each process can have its own unique sandbox, which gives it really fine-level control over what access it can have. In terms of stability or fault tolerance, again, since each XPC component is a separate process, if that process crashes or has a bug, that won't necessarily impact the main application or the other XPC components. The operating system could just restart that component automatically. XPC is used extensively by Apple in both frameworks and applications. So you can just grep the file system looking for XPC components. In terms of frameworks, for example, we can see WebKit. WebKit is obviously used by browsers such as Safari and does things like rendering and plug-in hosting. Again, it makes sense to use these or put these in separate processes, separate XPC components, because if you think about it, there's been a ton of rendering bugs, exploits, vulnerabilities. So if this is in a separate, really tightly locked down sandbox process, even if the attacker gets arbitrary code execution, they're not going to be able to do anything really useful like persist malware or do some command and control. They're then going to have to break out of the sandbox. Also, again, in terms of stability, for example, if a plugin crashes, if the plugin hosting is in a separate process, that's not going to impact the main browser. It might just say, hey, plugin was unable to load, but it's not going to crash Safari proper. Another example is applications. Again, iPhoto has a bunch of XPC components, again, related to rendering and converters. Again, this makes a lot of sense from a security point of view and stability point of view. If iPhoto is doing some rendering or doing some converting and that crashes, that's not going to impact the main iPhoto.application. All right, so here's a more detailed example. Allow us to kind of dig into XPC a little more. So say we have an example application that does three things. It downloads zip files from the internet, unzips them, and then displays the images that are in this zip file. Normally, we would write this as a single standalone binary that does all three tasks. What we can do though is we can convert this to XPC, basically break out its logical components. So here you can see we have a download XPC component, so this will be a separate process, and then we have an unzip XPC service, which will also be a separate process. So as I mentioned, each process can have its own set of privileges. So for the download XPC service, sure, this has to talk to the network, but there's no reason this has to talk to the file system. So we can put a sandbox constraint that says this process is not allowed to talk to the file system. We can lock down the unzip XPC service even more, saying it should not be able to talk to the network or the file system. So this means if an attacker is able to find a vulnerability in the unzip component and they get arbitrary code execution, can't really do anything useful. They can't persist malware. They can't talk out to the network. They then have to break out of the sandbox before they do anything useful. So again, it just adds an extra layer of stability. Also again, in terms of stability, fault tolerance, if any of these components have a bug and crash, that's not going to impact the main UI of the application. You can say, hey, unzip failed, but it's not going to be taken down if for example, the unzip XPC service crashes. So conceptually, how does this all work? Well, basically you have a client component, in this example, the XPC application. And what it does is it sends message requests to the XPC components or the XPC servers. These XPC servers or services will listen for messages, optionally authenticate clients that connect to them, and then process or handle their requests. Now, this should sound similar to something we're more familiar with, kind of the client-server networking model. There's a ton of parallels where you have clients talking to servers, authentication, all that kind of stuff. So conceptually, very similar. Message handling is processed by the operating system. Some of Ian's talks go into great detail about the low-level details of XPC. Basically, it's sent as mock messages. The operating system and the kernel takes care of everything. But from the application layer, you can basically just send a message and it'll get to the endpoint. So it's pretty easy to make an application or to make an XPC component. So make an XPC service. Basically what you do if you have an application in Xcode being Apple's IDE, you can just add a new target, and then for your target type you select XPC service. This will create the required files with some boilerplate code, and then also when you click build, it will be automatically packaged up into your application. Makes it really easy to deploy. One thing to mention, we can see a bundle identifier. This is a string that is used by the client, the application, to find the XPC service at runtime. Again, if we create parallels to this client-server networking model, this is kind of like the URL of the server or its DNS name. Again, this allows the client and the operating system to find the XPC service that the client wants to connect to and talk to. So how does an XPC service listen for client connections? Well, it does a few things. So first it creates this NSXPC listener object, sets its delegate, which is just a callback object, and then invokes resume. This delegate object has to conform to the NSXPC listener delegate protocol and implement a method called listener should accept new connection. This authentication method is called automatically anytime a client connects and allows the XPC server to examine and validate and allow the client. Again, this is all kind of similar to a server socket doing a bind, listen, accept. So now with this all set up and running, XPC clients can connect to the XPC server. Of course, the server or the service should expose some useful functionality. So here, for example, again, going back to our downloader application, this is the download image method. So once this is implemented, the XPC application will be able to connect to the XPC service and invoke this remote method. And again, if there's a bug or a crash in this method, it won't really affect the main client component of the application. All right, so back to the XPC application, the client. To use this service, the service we've now created, it needs to do two things. It needs to connect, obviously, and then invoke the remote methods. So it connects via the NSXPC connection init with service name and takes that bundle ID I mentioned. So it basically passes the name of the XPC server that it wants to connect to. This will return an NSXPC connection object. So then what you do is you call the NSXPC connection object's remote object proxy method. This returns a exported proxy object from the other side of the connection. So this is basically the server's remote object that's vended to the client. Now the client has basically a local copy of the remote object, and it can invoke methods directly on that object as if it was a local object. That will, though, be executed in the context of the remote XPC service. All right, so that's kind of the boring part. That's XPC basics. Let's dive into root pipe, which, as I mentioned, is an XPC-related privilege escalation bug. Now, what makes root pipe so interesting, at least to me, is not just the bug, but its timeline. So we can see that the bug was discovered by Emil in October of last year, where he responsibly disclosed it to Apple. I tested the code all the way back to OS X 10.5, which is Snow Leopard, and found that those operating systems were actually still vulnerable. I didn't have older versions, but if you look at some code, it appears that this vulnerability was actually introduced in the original release of OS X, which was in 2001. So subsequent slides will actually go into some other details. We'll see some malware that exploited this bug as a zero-day, and then we'll also talk about Apple's patching attempts. All right, so let's start by first looking at the vulnerability. So there's this private XPC service called write-config. It can create files. Specifically, it exposes a remote method named write-config-dispatch create files with contents. Yeah, nothing too special yet. The problem is, or was, any user, even guests, can connect to this write-config XPC service, which runs as root, and then can create files. And the user could specify the path, the contents, and the attributes. Obviously, this is really not good. So for example, we can create a copy of a shell and set the SUID bit. And then since that shell is going to be copied as, or created as root, simply executing it will give us root privilege. Really doesn't get much easier than this. All right, so now let's detail exactly how we can connect to this write XPC service and invoke the vulnerable method. So kind of go into the details of what happens under the hood when we perform this exploit. So while we could talk directly to that remote XPC service, the write-config XPC service, which has that vulnerable method that allows anyone to create a file, it turns out that there's some client code within an Apple private framework called system administration that we can utilize. This just is kind of another layer of abstraction, but it makes it easier to talk to the remote XPC service. So step one, we need to get access to a write-config client object. As its name suggests, this is a client object that's built specifically to talk to the write-config XPC service. So specifically, we call the write-config client's shared client class method, and this will return us a singleton instance. All right, so now with this client object, we can connect to the remote write-config XPC service. We do this via the write-config client authenticate using authentication sync method. If you look at the disassembly for this method, you can see some of the low-level XPC functions we talked about. So for example, you can see init with service name. So under the hood, this method actually makes that connection to the remote XPC service. Now, as I mentioned, when you make an initial connection to an XPC service component, it's going to authenticate you first. Now, one of the vulnerabilities or issues with this bug that actually allowed guest users to exploit it was the fact that you could pass in nil for this authentication object. In Objective-C, if you have a nil object and you execute methods on this, this doesn't throw a null pointer exception. It just kind of goes off into the ether. Now, as we'll see, actually older versions of OS X did not allow nil to be passed in as this parameter. And you had to be an admin to create an authentication object to pass. So actually, older versions of OS X were more secure. Go figure. All right, so now we've authenticated. We want to invoke the remote method to create that SUID file. Remember, you need to get a proxy object, which is the exported object from the server side of the connection. And then once you have this, then you can invoke remote methods on it as if it was almost like a local object. So the write-config client has a remote proxy method, which gives us back a dispatcher object. And then we can pass requests to the remote object. So again, since we're using this kind of local abstraction, we don't get the remote object directly, we get a local dispatcher object. But basically, when we invoke methods on this dispatcher object, it'll get sent to the remote XPC service. All right, so locally you ask the dispatcher object to create a file with the createWithFile content method. Under the hood, a little more goes on. This invokes the forward invocation method of that local dispatch object. As we see in this, it's going to do some forward invocation. It's then going to get the remote proxy object itself and pass our message. So again, end result, we call the remote method we want, the vulnerable method, on this local dispatch object. It'll transfer it over to the remote object and create our attacker file. So putting these steps all together, we can create a shell or any other file as root with any attributes, set UID bits or anything else we want. So again, the steps, just to reiterate, are first, we get an instance of the write config client object. Then we authenticate, which again, anyone can do, even guest users. We then get this local dispatch object, and finally, using this local dispatch object, we invoke the remote method that allows us to create the file. Now, if we execute this all, we can monitor what goes on, at least at the file level, by running a tool such as fs usage, which shows file IO. So first we can see our application, which is just called root pipe, that's triggering the exploit. We can see it makes a copy of the shell. We use ksh because that allows itself to be run as root. And then if we look, we can see write config. This is the remote XPC component, the private XPC component that has the vulnerability. We can see it creating a copy of that file and then chmodding and choning it so that it has the SUID bit set. So older versions, just to briefly mention, they do require you to be an administrator. The default user on OS X has these privileges. So again, this is still a privilege escalation because it allows an attacker to get root privileges without having to specify a username and password. All right, so recall the timeline. Emil found the bug in October, reported it to Apple, but turns out that there was some malware that was actually exploiting this vulnerability as a 0-day before Emil's discovery. So XSL CMD is an OS X persistent backdoor. It was submitted to VirusTotal in August 2014. Of course, no AVs detected it, but a few months later, FireEye came out with a report. I guess they did some back-end analysis on this file. Basically determined that it was a new piece of APT-related OS X malware. As I mentioned, standard backdoor provides some sufficient features. It provides the attacker the ability to create a reverse shell, screen capturing, and then keylogging, which will be important in a second. Now, one interesting thing is in the report there was no mention of any local privilege escalations. I don't think that they were withholding it. I just think their analysis completely missed it. That's my opinion. So after Apple patched the vulnerability, Emil wrote a nice blog kind of detailing the bug. And someone went back and was doing some analysis on this malware and actually found out that this malware appeared to exploit the same bug, which kind of intriguing. We don't see a lot of OS X malware, and we don't see a lot of OS X malware that actually has 0-day privilege escalation vulnerabilities built in. So why was malware attempting to escalate its privileges? So on OS X, user mode code can capture key presses if the access for assistive devices is enabled. Now you can enable this via the UI under system preferences, but you have to be root to do this. So as a normal user, if you click on the checkbox to enable this, it's going to throw up a prompt and you're going to have to put in your username and password. So you can, as I mentioned, do this via the UI, and if you monitor what this does under the hood, it basically creates a file named accessibility API enabled in var.db that contains a single character A. This is just a marker file that the operating system checks, and basically if that file is there, it says, okay, user mode code can do keylogging. It can intercept or capture key presses. So if we look at the disassembly for the malware, we can see it is actually creating this file. So in other words, it's using the root pipe vulnerability as a 0-day to create this file so that it could do key capturing and key logging. Kind of cool. All right, so I mentioned again, Emil reported this bug to Apple in October. It took him about 6 months to release the initial patch, which, as we'll see, was insufficient. Eventually, they did release a new patch, so I think they may have finally got it right, but it's kind of a rocky road to get there. So the first thing Apple did, which I think somewhat of a fail, was they decided not to backport their patch. And in the quote they released, they basically said, it's too much work. However, Pedro, OS X Reverser, released a dilib for Mavericks, which again was an OS that Apple decided not to patch, that would monitor for connection attempts and basically ignore untrusted clients. I think it's kind of funny or sad when independent researchers can help secure users more than the vendor. Anyway, so Apple did patch Yosemite, which is good. And so let's look what that patch did. Basically, they left the write config XPC service completely intact. They left that function that can create files completely intact. Basically, what they did or what they said was, we're only going to let Apple processes talk to this. So it's like almost they added a security guard at the door that basically said, hey, if you want to talk to me, if you want to create a file, I'm going to check your badge, your ID, and basically say, hey, if you're not Apple, GTFO. So in the diagram, we can see if untrusted or unsigned code, a hacker tries to connect to this XPC service, it's going to block it now, not let them in. But if an Apple process tries to connect, the security guard is going to be like, yeah, sure, you can connect and you can create whatever file you want. So recall when a client connects to an XPC service, the listener should accept new connection method will be invoked. This allows, as I mentioned, the server to examine the client and allow or deny. So what the patch did, it checks that the clients have a new entitlement, which is com.apple.private.admin.write-config. And we'll talk about entitlements in a second, but let's first take a closer look at this authentication method. So we can see what it does is it grabs the client's authentication token. This is something that the operating system automatically generates when you try to connect to a remote XPC service. And as far as I know, you can't spoof it. It then checks if the client has this entitlement, the com.apple.private.admin.write-config client. And if it doesn't have this entitlement, it basically doesn't let it in. So again, you can kind of think of this as a security guard checking badges at the club, and if you're not an Apple employee, you don't have the right entitlement, they're not going to let you in. So what are these entitlements? Well, they're basically just embedded blobs that are in the code signature of an application. And they confer capabilities or permissions. So it's a way to kind of tag an application and give it special permissions, kind of like specifying what employer they are. So again, when the security guard checks, it can determine if they're allowed or denied. So Apple's patch looked weak to me. Instead of like appearing as a security guard, it looked more of like a mall cop. So I had a long flight home from Infiltrate, and I always wanted to do something cool on an airplane, besides obviously hacking the airplane. So I took a little bit of a closer look at Apple's patch, and it turns out that it was insufficient. So this is a brief video. Basically see, I execute the ls command. Okay, cool, it's showing up there. I look for a file named Phoenix. It's not on the root file system. I try to create it. I'm not root, so it tells me to take a hike. I then execute a small Python script that does a few things. It says it's done. I relist this file, and we can see that now it's been created in the root directory. If we ls it, we can see that it's owned by root, which makes sense because that XPC service is owned by root as well. And then we can see any contents I wanted in this file can be put in this file. So at the time, this was on a fully patched system. This was after Apple released their initial patch. So I want to walk through how I was able to bypass Apple's patch, what failed and then what worked. My goal was simple. Since the XPC service and that vulnerable function was left untouched, I just wanted to be allowed to talk to it, to connect to it, to authenticate it. And since authentication was based 100% on the binary connecting, if the binary is trusted, any code within that binary is able to talk to it as well. So if you can inject some malicious code, get it to load a malicious plugin, anything like that, the operating system, the check only was checking that the main binary that was connecting was entitled. So this is what I tried, and we'll kind of go through all of these. I first tried to create my own entitlement, try to spoof that. I tried to infect signed, trusted, entitled binaries. I tried doing some runtime process injection, hijacking entitled binaries, and then finally trying to load malicious plugins. So we'll look at each of these closer. So the first thing I tried to do was to add the com.apple.private.admin.write config entitlement to my own binary. Again, this is what the security guard at the door is basically checking. If you have this entitlement, you will be able to talk to the XPC service and then still retrigger the vulnerability. So in Xcode, you can specify entitlements. So I was like, well, let me try to put this new Apple private entitlement. And it let me compile my binary, but as soon as I executed, the OS told me to, GTFO. It basically said, hey, you claim to have this Apple entitlement, but I can't verify you. So I'm not sure exactly how this verification all works, but I imagine since it's a private Apple entitlement, it can probably detect that I'm not a verifiable Apple binary, so it can kick me out. So basically it can be like, this is a fake ID. You're not really an Apple binary, therefore you can't have this private Apple entitlement. So since I can't fake the entitlement, I have to abuse a legitimately entitled binary. Now, not all Apple binaries are entitled. So these entitlements kind of like an extra layer, more fine-grained permission control that be slapped on certain binaries. So what I did was I wrote a small Python script that could enumerate all the binaries on the operating system, on my file system, and give me a list of which ones were entitled. This gave me about 50 or so. And again, these are the trusted binaries that are allowed to connect to the remote XPC service. So my goal was then to try to coerce any of these to load my arbitrary malicious code, because again, once I'm in the trusted context of any of these processes, I can then reconnect to the XPC service and re-trigger the vulnerability. So the first thing I then tried to do was simply infect an entitled binary. Unfortunately, the mock-O loader verifies that digital signatures of binaries are intact. So here we can see me trying to infect the directory utility application, which is entitled and thus allowed to talk to the XPC component. But you can see that when I execute it, the loader basically says, hey, the digital signature is no longer valid, and just kills the process right out. Now it turns out on OS X you can unsign binaries and then they are still allowed to execute. But when you unsign a binary, it basically removes the entitlements as well, because the entitlements are part of that digital signature. So that's really doesn't gain you anything either. I then tried to coerce the loader to load a malicious dylib into an entitled process. So OS X has some environment variables. For example, it has the dyld insert libraries environment variable that tells the loader to load a malicious or any dylib at load time. This is kind of like LD preload on Unix or Linux systems. But it turns out that environment variables are ignored for entitled binaries. So here's the source code from the OS X's dynamic linker loader, dyld, and we can see it calls a method that's named prune environment variables. And the Apple comment says, for restricted binaries, delete all dyld and LD library path environment variables. So what is a restricted binary? Well, it's a binary that has the SUID bit set, or it's also an entitled binary. So basically, the mock-O loader will strip away and ignore any environment variables if the binary is entitled. And since we're targeting entitled binaries because we need that entitlement to connect to the XPC service, it's basically going to ignore this, so this doesn't work either. So I then tried dylib hijacking. Dylib hijacking, kind of neat attack. I talked about it yesterday at DEF CON. Well, this conference. And basically what you can do is you can, if you find a vulnerable application, you can coerce it to load a malicious dylib, even if the dylib is unsigned. Unfortunately, I guess a limitation of this hack is you need to find a vulnerable application, or you can only exploit vulnerable applications. You can't hijack arbitrary applications. So I wrote a tool that could look for all binaries on the file system that were vulnerable to a dylib hijack, but unfortunately none of the binaries that were vulnerable had the entitlement. So this didn't work either. I then thought I'd try runtime code injection to inject malicious code into an entitled process that was ready running. So the way you do code injection on OS X, pretty simple, takes about 5 steps. You first get a task for the PID. This is kind of like access to the remote process. Once you have this, you can inject shellcode, you can allocate memory for stacks, you can create remote threads. Unfortunately, in order to get access to this remote process, even if it's running as the same user, you need to be root. So basically Apple says if you're doing any kind of code injection, you got to be root, which from a security point of view, my opinion, makes complete sense. So since we don't have root, we're trying to get root, this also doesn't work. I then tried to find an entitled application that could load plugins. I figured maybe I could plant a malicious plugin and then get loaded. And then again, once I'm loaded, I'm in this trusted entitled binary, and then my malicious plugin can reconnect to the XPC service and re-trigger the vulnerability. So here we have the directory utility. It's entitled, which means it can talk to the XPC service, which is good, and it appears to support plugins. Specifically, if we look at its application bundle, we can see an internal folder that's named plugins. So I was intrigued. So I disassembled directory utility binary, and you can see it invokes a method named load plugins in directory. If we run a file monitoring tool, again FS usage, which monitors file I/O, we can see that when you execute the directory utility, what it does is it goes through all plugins in its internal bundle folder and yes, loads and executes them into memory. Again, seems promising. So I then tried to install a plugin by copying it into the directory utilities plugin directory. Now, since directory utilities is a system application, it's actually owned by root, so you have to authenticate to even install a plugin. But let's forget this fact for a minute, because basically I want to say, if I found some way to copy in or install a plugin, would directory utility load my plugin? I mean, it's an unsigned malicious plugin. Maybe directory utility is doing some extra checks. So I manually authenticated, installed it, and then when I execute it, you can see that directory utility found my plugin, and even though it was unsigned, it loaded and executed. So we're kind of closer. I mean, we can get this entitled binary to load unsigned malicious code that then can talk to the remote XPC service. But since we need to be root to install the plugin, since directory utility is root, you know, this is really not any closer at all. But if we can get directory utility to not be owned by root, we can then copy and install a plugin, execute it, and then in theory be able to re-exploit the vulnerability. So it turns out we can change the ownership of the directory utility, and thus we can install a malicious plugin, game over. So this is how I bypassed Apple's initial patch. 3 easy steps, really not that complicated. So first you copy the directory utility into the temp directory. On OS X, when you copy a file to the temp directory, its permissions get changed to the current user. So it gets changed from root to me. So this means now I can put plugins into its applications bundle because now I own the application. So we drop a plugin there, and then we simply execute directory utility. This loads the malicious plugin, even though it's unsigned, and then our malicious plugin can make the XPC request to the remote XPC service. Again, the security guard at the front door is going to check and say, hey, wait a minute, I'm not allowing anyone just to come in and re-exploit this. He's like, who are you with? And I'm like, well, I'm with directory utility. So security guard goes and checks directory utility, says, okay, yes, you are executing within directory utility. Okay, directory utility is an Apple application and it contains the correct entitlement. So go ahead, you're able to do that. So this means we can trigger the exploit once again. So here's the Python code for it. Super basic. I wish all privilege escalations were this easy. Basically 3 simple steps. So again, you can see Python code. We copy the directory utility applications to the temp directory. This makes it owned by us. We copy in the malicious plugin. Again, we're not modifying the digital signature of the application. We're just planting a plugin in its plugin directory. And then we execute it. This will give us root. So I reported this bug to Apple. They fixed it in OS X 10.10.4, CVE 2015-3673. When I had posted the video showing that I was able to bypass that, I didn't want to release details before Apple fixed this. But this inspired Emil, the original founder of RootPipe, to look as well, and he actually found the same issue. So he shares the CVE with me, which is kind of cool. So here's some control flow graphs that kind of illustrate Apple's patches. So we can see in the original version of OS X 10.10, this is the listener should accept new connection function. Again, this is what is authenticating clients. So we can see at the very beginning, there's no authentication. This is a control flow graph. There's no checks being done. Basically, anybody, even if you're a guest, is allowed to talk to the XPC service. In 10.10.3, this is their initial patch. You can see they added some more checks. As we just showed, these were insufficient. And then finally, in OS X 10.10.4, you can see the complexity of their checks got way more. And as we'll see, I think they got it right. But this is, kind of shows how hard it is to get things right. I would hope Apple would have got the initial patch right. They didn't. But, security is hard, so I don't want to pick on them too much. So briefly looking at Apple's most recent patch, we can see it does a few things. We can reverse engineer it to figure out what it's doing. So the first thing is they add some extra private entitlements. I think this just gives them more fine-grained control over who's allowed to connect. Most importantly, though, they say the binary that's connecting has to live in either system or /user. Now, these are both owned by root, so our attack generically is thwarted. We can't copy out these applications, change anything, and we also can't put plugins or malicious code in any of these directories because these are owned by root. And again, we don't have root, we're trying to get root. So I don't see any immediate issues with the patch, but as Pedro states, there's still the fundamental issue that the whole fix seems kind of brittle. So as Pedro says, the problem of their fix is that there are at least 50 plus binaries which are entitled, which are still allowed to talk to the XPC service. So a single exploit in any of these binaries and the system is owned again because there's no fundamental fix inside write config. So I really wouldn't be too surprised if someone found again a way to exploit this. All right, so we've seen that OS X contained a trivial privilege escalation that perhaps was introduced in the very inception of OS X in 2001. We saw malware that exploited this as a zero-day vulnerability. And Apple's initial patch, in my opinion, was crap. So these things scare me. I love my Mac, but I don't want to get hacked. So I briefly want to talk about some free security tools that I run to protect my Mac that I share with others to hopefully protect their Macs as well. So my side hobby, I run a small OS X security website. I have a nice little malware collection, including the one I mentioned today, XSL.cmd, that exploits this vulnerability or exploited this vulnerability as a zero-day. I found it hard to find a good collection of OS X malware. People who have these samples generally don't like to share. So I try to make a nice collection that anyone can download and play with. And then, as I mentioned, some tools to protect my Mac. That I figured I should share. So I briefly just want to share them with you guys today. So the first tool I wrote is called Knock Knock. Simple goal, when I say knock knock, it should tell me who's there. It basically tells you all software that's persistently installed on your computer that will get automatically executed whenever you restart your computer or log in. Conceptually, exactly the same to auto runs on Windows, but in my opinion, looks a little better. My favorite feature is probably the virus total integration. The tool doesn't actually tell you if something is malware or not. It's malware agnostic. It just shows you what software is persisting, which is good because then if some new malware comes along and persists, which all OS X malware I've seen does, it will be able to show it to you as well. But with the virus total integration, this is kind of nice because for known malware, it can detect and flag this. You can also submit files to virus total, view the scan results. Kind of cool. Now, the only limitation, in my opinion, to Knock Knock is that it's reactive. It doesn't provide real-time protection. So I wrote another tool that can provide that. So I wrote Block Block. Now, Knock Knock tells you who's there. Block Block tells you when someone is moving in. Basically, it provides real-time runtime protection, monitoring known persistence locations. You can kind of think of it as a firewall for auto-run locations. So anytime something persists itself or installs itself, it'll pop up and you'll get a little warning that you can either confirm or deny. Now, I released this beginning of January, but it's been kind of cool because as new OS X malware samples are released, I've been able to test them and they've all been generically detected by this tool. So here we can see hacking implants persistent OS X implant. This basically means if you had already been running Block Block and hacking team tried to target it, you would have got a pop-up. Now, you know, my mom and dad are still going to click allow, but as security conscious users, hopefully we would at least examine this and in this scenario click block. Another piece of malware that was released a few days ago, Stefan Esser released a 0-day vulnerability. A few days later, there was some malware that was exploiting it. This, in my opinion, is a very good example of why it's not good to irresponsibly disclose bugs. The malware authors were just like adware writers. They're not sophisticated adversaries. They're going to be finding their O-days. So as security researchers, when we release O-days, there is negatives to that. And in this case, you know, there's adware authors that are now targeting you know, innocent Mac users with this privilege escalation vulnerability that Apple is working on to fix but is not yet patched. So again, though, if you were running Block Block, even though it wouldn't detect the exploit, it's not designed to detect exploit, you would be protected because when the malware, even though it's running as root, goes to persist, you get a nice little pop-up. All right, the last one I want to talk about, another one I just released at Black Hat is called Task Explorer. This is conceptually similar to Process Explorer on Windows. In my opinion, it's a kind of a better activity monitor, again, for security-conscious users. Got some nice features. For example, you can see all the processes that are running that aren't Apple, that aren't signed, so you can quickly filter those out. It shows you the signing information, so you can see if things are unsigned. Virus total integration, and then in the bottom pane for each task or process that's running, you can see the loaded dilibs, the files, the network connection. So I actually used this tool to help me find this vulnerability because what I did was I ran it and then I looked at the plugins that were loaded by directory utility. And then when I planted my malicious plugin, I could see that it got loaded. All right, so let's wrap this all up. Just some brief conclusions. So first, my humble opinion, I think OS X security is kind of lame. You know, there's a lot of public 0 days. Apple's malware mitigations can be bypassed. Yeah, then there's probably a lot of trivially exploitable bugs such as root pipe that are out there. And again, since root pipe was kind of in the inception of OS X, you know, again, that bothers me. So it's a great idea to audit all things. As security researchers, I think that's one way we can kind of help out Apple, or at least selfishly make our Apple computers more secure. So it's a great idea to audit these XPC interfaces, right? Apple kind of thought that since this was a private XPC interface, maybe no one will look at it. But as soon as someone started poking around, there was a trivially exploitable bug that was found. It's also a good idea to really thoroughly analyze OS X malware. The initial FireEye report did not mention the O-Day that was in it. I believe that they just missed it. But again, that to me says that we should be doing a little more of a thorough job analyzing malware. There's not that much OS X malware out there, so let's do a good job. And then finally, when a security vendor releases a patch, we've seen Microsoft do this in the past too, I think it's good to audit this patch to make sure does it really address the issue. You know the bad guys out are doing the same thing. The nation state guys, the advanced adversaries. So again, I think we have some responsibility to audit these things because unfortunately we can't really count on the vendor at this point. All right, so thanks for your time. You can email me. I'm on Twitter. These slides should be up shortly to download. And also check out synac.com if you guys want to get paid to do some legal hacking. So we have about five minutes. Are there any questions? Yes, sir. So the malware actually only used it, or I only saw the malware using it to enable keylogging, which was surprising. I thought could have used it far better to do more surreptitious things, but it's, I think they used it for what they needed. So the malware, yeah, just basically seemed to use the exploit only to enable keylogging. Yes. Yeah. So the question was, the DoD, I think it was the NSA, used to release articles or documents how to lock down, how to secure your Mac. And they haven't done this for a certain number of years. This question is why. I'm not sure. Yeah, I would like to see that too, because they were actually pretty good. They had good suggestions. I have no idea why they don't do that. Sorry. I'll email some of my NSA contacts and ask them. No, I don't think they talk to me anymore. But they just heard that, so maybe we'll get an answer anyways. All right. Well, thank you guys. I really appreciate attending. Email me or chat to me if you have any other questions.